Students, today we will discuss about properties of convolution. The first property is commutative property for continuous time systems. If I have an input x of t and the system h of t, the output is yt, then that means yt is x of t convolved with h of t. This is equivalent to if we exchange the system and the input, that means the system, the signal for the system will become an input and the input will become a system. Then this will be h of t convolved with x of t, and I will get yt. The two outputs are the same. So that means x of t convolved with h of t is equal to h of t convolved with x of t. In the first case, the integration will be from minus infinity to infinity x tau ht minus tau d tau. In the second case, it will be from minus infinity to infinity h tau xt minus tau d tau. So this property is useful because in some cases it is easy to do the integration by making integration from minus infinity tau ht minus tau d tau, or in some other cases it is easy to do it in the form where y of t is h of t convolved with x of t from minus infinity to infinity h tau xt minus tau d tau. This is one example. For example, here I have y of t is equal to ut convolved with ht. It's the same as ht convolved with ut. If we take the second case, it means from minus infinity to infinity h tau ut minus tau d tau. So this will be from minus infinity to t h tau d tau, the integration of the system. Okay, here in this case, the one which will flip and slide is u of t. Yeah, and in the second case, if I do it this way, the one which will slide in the flip is ht. Distributive property, if I have xt convolved with h1t plus h2t, this is the overall system, one system, and I have an output here. You can overall system into two subsystems where you have an output y1t and y2t. That means y1 of t is x of t convolved with h1 of t, and y2 of t is x of t convolved with h2 of t, and the overall output is given by this. Again, these properties are useful to simplify computation of convolution. And for example, in this case, if I have a complex system, I can break it into two subsystems, simpler subsystems, and I can perform the convolution integral. Okay, and the next is associative property. If I have x of t convolved h1 of t convolved with h2 of t, that means first we do here h1 of t convolved with h2t. It will be the same as first you do x of t convolved with h1 of t and then with h2 of t. Or in other words, if you exchange the order of, because of commutativity also, the order of the two systems, the first here was first h1 and second h2. So if you change it first h2 and then h1, the result will be the same. The output yt will also be the same. Another property is memoryless system. If you remember in the first chapter, we say a system is memoryless if the output at the present time depends on the input, on the value of the input at the present time, or the output at time t depend on the input at time t. In this case, in the second chapter, we have a different definition. H of t is equal to 0 for t different from 0. So if h of t is equal to 0 for t different from 0, we say the system is memoryless. What kind of system will give you this? For example, h of t is equal to k times Dirac t. Remember what is Dirac t? Is the impulse function which is equal to infinity at t equals to 0 and 0 otherwise. So if you convolve, for example, if I want to calculate, if I have a system like this, and I want to calculate y of t, and I have an input xt, so y of t is x of t convolved with h of t. That means x of t convolved with k times Dirac t, but Dirac t convolved with xt is equal to xt itself. So the output will become k times xt. That means here the output at time t depends on the input at time t, so which makes it memoryless. Note that both definitions, the definition here based on the system and the previous definition in chapter 1 based on the input and output relationship, the two will give you the same result. Okay, invertibility. Invertibility means the inverse system connector in series to the output should reproduce the original input. Okay, so if a system is invertible, if I cascade the original system and its inverse, then at the output I will get at the input x of t. So here in this case here, what is the overall system? The overall system will be h of t convolved with h1t. Okay, if the overall system h of t convolved with h1t gives me Dirac t, then I say h1t is the inverse of h of t. And the output in this case will be x of t convolved with what is the overall system? Dirac t. X of t convolved with Dirac t will give me x of t. Okay, so a system is invertible. So if I have a system H, it has its inverse h1 of t if h of t convolved with h1 of t is Dirac. The other property is causality. If you remember in chapter 1, we say a system is causal if the output at time t depends on the present input or the previous input or present and previous input, but not on future inputs because of the cause and effect relationship phenomenon. So in this chapter, we defined it in another way with considering the system. A system is said to be causal if h of t is equal to 0 for all t less than 0. What it means, we just look the system impulse response, and if we know that h of t is equal to 0 for t less than 0, then we say the system is causal. That's all. And stability. What about for stability? A system is stable if its energy is finite. That means from infinity to minus infinity, h of tau square d tau is less than infinity, or without the square, from minus infinity to infinity h tau, absolute value of h tau d tau is less than infinity. We call this absolutely integrable system. So in that case, bounded input will give you bounded output. For example, here a sufficient condition for to be a stable system. First, we have bounded input. Absolute value of x of t is less than x max, which is less than infinity. Then the absolute value of y of t is the absolute value of this. If we say this means this is less than or equal to x max, okay, we substitute for x tau x max here, and this should be less than infinity, which means x max is positive. Now, therefore, this integral function should be less than infinity. So that means the impulse response should be absolutely integrable. Okay, we will see some examples for in the notes. Let's go to the additional class notes. So a system is causal if h of t is equal to h of t is equal to 0 for t less than 0. For example, let's have this h of t is equal to ut. This is unit step function, and we know that unit step function is equal to 0 for t less than 0. Therefore, this system is causal system. If we try to relate the input and the output, let's try to relate the input and the output. Y of t is equal to x of t convolved with h of t from minus infinity to infinity x tau ht minus tau d tau. H t minus tau means ut minus tau d tau. That means you have unit step first, u tau. Okay, this one, and if you flip it, when you flip, you will get u minus tau, okay, from minus infinity to 0, and then you slide it. For example, I slide it to the right, and it will be from minus infinity until t, okay, for the shift t is greater than 0. So I have here ut minus tau. If I multiply by any signal x tau, what will happen? The result of the product will be x tau from minus infinity until t, because the value of ut minus tau is amplitude is 1. So it doesn't change the amplitude of x tau. So it will be from minus infinity until t x tau d tau. So the unit step function gives me the limit, helps me to know the limit of integration from minus infinity to t. So you see, y at time t depends on previous values of x until present value of t. So the system is causal. If I have ut plus 2, ut plus 2 means shift to the left by 2, and it starts at minus 2. Obviously, this system is not causal because h of t is different from 0 for t less than 0. Stability, as we said, a system is stable if the integration from minus infinity to infinity ht dt is less than infinity. Let's have this example. H of t is equal to e to the power of minus 2t ut. That means let's do the integration from minus infinity to infinity e raised to minus 2t ut dt. Because of ut, we start from 0 to infinity e to the power of minus 2t dt, and we use the rule of integration, and we will have this from positive infinity to 0 means e raised to minus infinity minus e raised to 0, and this will be 1 over 2. 1 over 2 is less than infinity. So that means it satisfies the absolute integrability condition. So the system is a stable system. On the other hand, if I have h of t e to the power of 2t ut, again we apply the rule of the integration again from minus infinity to infinity. That means from 0 to infinity, 1 over 2 e to the power of 2t. So this is e raised to infinity, which is equal to infinity. So the result of the integration is infinity. That means the system is not stable. The system is not stable means Even if I give bounded input, then the system will give unbounded output. Okay, now the next is unit doublet, unit step, and unit ramp. Okay. Let's have here the slides, notes from the slides. If you remember, an impulse, the way we define it, an impulse is Dirac T is it is a small rectangular pulse of duration delta and amplitude 1 over delta. So Dirac T is equal to the limit as delta goes to 0 of this. Okay, because when delta going to 0, 1 over 0 goes to infinity, and this pulse will be located at 0. Now, a unit doublet function is called the differentiator. So the differentiator function, if I make the derivative of this, I will have 1 over delta at 0 and negative 1 over delta at delta. Okay, at delta. So I have this. This is 1 over delta and negative 1 over delta, two impulses here at 0 and delta. If I convolve it with x of t, the input, then I will have x of t minus x of t minus delta divided by delta, which is the rule of differentiation. The rule of differentiation. So that's why we call it, this is the unit doublet function or the differentiator. Symbolically, we write it as u1 of t. u1 of t is d by dt of Dirac T. Okay, so if I cascade so many differentiates, of course, if I have n differentiators, I will have the nth derivative of x of t. Another is the integrator. The integrator function is, as we see an example before. So the u minus t, it is unit step, so it's denoted as u subscript minus 1 t. This is just a notation, okay? Don't be confused. It's a notation. So minus 1 of t is equal to ut, the unit step. If I convolve x of t with u minus 1t, which is unit step, I will have from minus infinity to t x tau d tau. Remember this system? This system is integrator. So the impulse response of an integrator is u of t, unit step function. If I cascade so many integrators, okay, n integrators, then I will have the integration of n times integration. For example, if I cascade two integrators, and let's find the overall impulse response. So I have two integrators, one integrator here, another integrator here. So the notation for it is u minus 2 of t. From the first integrator, I will have unit step function, okay, because Dirac T convolved with u of t is equal to u of t. So in the second integrator will be the integration of unit step, okay, u tau. So if I do the integration of unit step, if t less than 0, it will be 0. If t greater than 0, it will be t. So it will you will get t times ut. So if I have n integrators, the impulse response of the system will be t the power of n minus 1 factorial times ut. If I have u1 of t and u minus 1 of t, that means the first one is a differentiator, the second one is an integrator, unit step function. That means the derivative of the unit step function, it will give me Dirac T. And this notation is, we call it u0 of t. u0 of t is Dirac T. Okay, so u minus 1 of t is a unit step function. Let's prove the two integrators. two integrators. So the first one is unit step, the second unit step, and let's find the impulse response. Y of t is Dirac t convolved with h of t. The overall impulse response is h of t, which is equal to h1 of t convolved with h1 of t. And in the first one, the first output is Wt. Wt is Dirac t convolved with h1t, which is equal to ut. And the second one, Wt convolved with h2t, ut convolved with ut. That means we apply the rule of convolution. It will be u tau, ut minus tau d tau. So we flip u tau and we have u minus tau and we shift it. So if t is less than 0, this product is 0. So the result is 0. If t greater than 0, okay, if I multiply by u tau, this one by u tau, the result will be the result of the non-zero result will be between 0 and t. Okay, if we multiply by unit step function, this one, okay, this is ut minus tau multiplied by u tau. U tau starts from 0 to infinity, but if you multiply these two functions, you will have non-zero value between 0 and t. The rest will be 0. So it will be the integration of d tau from 0 to t, and this will be tau, and it will be equals to t. So we have two cases. If t less than 0, the result is 0. If t greater than or equal to 0, the result is t. How I write it mathematically, y of t is equal to 0. For t less than 0, y of t is equal to t. For t greater than or equal to 0. And this is t times ut, and we call unit ramp function. Why it is called unit ramp? It's like if you see it, it looks like a ramp, okay? And unit means the slope is 1. Slope is 1 because this is t. So when t is 1, y is 1. When t is 2, y is 2. That means the slope is 1, and we call this the unit ramp function. And symbolically, we write it u subscript minus 2t. U subscript minus 2t. Okay, now let's have one example how we use these properties. For example, I have this x of t. This is the signal x of t is 0 from minus infinity to minus 1. It is equal to 1 between minus 1 and 1. It is equal to minus 1 between 1 and 2. It is equal to 0 for t greater than 2. Okay, this is x of t. And this is h of t. H of t is equal to 0 from minus infinity until 1. It is 1 between 1 and 2. It is 0 for t greater than 2. Let's say I want to compute x, if I have x of t this and h of t this, I want to compute the output yt, which is x of t convolved with h of t. Okay, x of t, I can write it in terms of unit step function. You can check this. It means ut plus 1. Ut plus 1 starts at minus 1 minus 2 times ut minus 1. Ut minus 1 starts at 1, remember, minus 2 here, ut minus 1 plus ut minus 2. Okay, this is if I want to write this x of t in terms of unit step function. This unit step starts from minus 1. This unit step starts from 1, and this unit step starts from 2. Okay, negative 1 and point and 1 and 2. That means now the output yt is x of t convolved with h of t. I can write it also. Yt is u minus 1 of t. What is u minus 1 of t? The differentiator, d by dt of Dirac t. Convolve u1 of t u1 of t is the integrator, the unit step function. Convolve x of t, convolve with h of t. Why? Because u minus 1 of t convolve u1t. Okay, u minus 1 of t is the differentiator, d by dt of Dirac t, convolve with u1 of t, unit step, it will be d by dt of ut. d by dt of unit step, it means Dirac t. So this overall, this one will be Dirac t. Okay? So Dirac t convolve any signal will give me the signal itself. So it's like multiplying in normal algebra, multiplying a number by 1. If you multiply any number by 1, it will give you the same number, like that. So if you convolve an impulse with this convolution, x of t convolve with h of t, it will be x of t convolve with h of t. So it doesn't change the result. But it helps us, you see, now u minus 1 of t is here, convolve with u1 of t, convolve x of t, convolve with h of t. All right? So we can, for example, we can first do the derivative, okay? We can make u1 of t convolve with x of t. u1 of t means d by dt of ut, and u minus 1 of t is unit step. So these two will give me Dirac t. So u1 of t is d by dt of Dirac t. Convolve with xt means d by dt of x of t. So this together is d by dt of x of t. So d by dt of x of t means the derivative of this. The derivative of this is the derivative of unit step is unit impulse. So Dirac t plus 1. The derivative of this is Dirac t minus 1. The derivative of this is Dirac t minus 2. So I did first this, and I get Dirac t plus 1 minus 2 Dirac t minus 1 plus Dirac t minus 2. So it's very easy now to convolve this result with h of t, because convolution with an impulse is easy. For example, now if I convolve this with h of t, it will be h of t plus 1. If I convolve this with this, minus 2 times h of t minus 1. If I convolve with this, h of t minus 2. Then finally, I have here outside u minus 1t. u minus 1t means unit step function. So I pass it to, I convolve it with unit step, means I do integration of the overall result here with respect to tau. So in the integration of this from minus infinity to tau, and whatever function I have here, d tau. Okay, so the derivative of x of t convolved with h of t is this, and then I have ht plus 1 minus 2 ht minus 1 ht minus 2. ht plus 1 means shift of h of t by 1 to the left, so I have here, and 2 times ht minus 1, and ht minus 1 means shift of h of t by 1 to the right, so I have this, and minus 2, because of that the amplitude is minus 2, and ht minus 2 is this one. This is the result of this. Okay, now after this, what's the last step? U minus t. Okay, u minus t, okay, means u of t convolve everything. That means the integration, as I said, of from minus infinity to t of this value. So we do the integration of this from minus infinity to t. Okay, this is axis will become tau. So we will have different cases. For example, for t less than 0, the result will be 0, because for t less than 0, this one is 0. And when t is between 0 and 1, it will be the integration of. Okay, when t is between 0 and 1, it will be the integration from 0 to t of d tau, which is equal to t. And when t is between 1 and 2, I have two integrations from 0 to 1 d tau and from 1 to t d tau, from 1 to t between 1 and, if t is between 1 and 2, the result here is 0. So I have the result 1. And if t is between 2 and 3, I will have from 0 to t x1 tau d tau, from 0 to 1 d tau minus 2 from t over 2 d tau, which is 5 minus 2t. And you can go through this, and finally the final result will be like this, and you can plot it, this result. Okay, that's all about properties. Thank you for listening to this lecture, and we will continue with the next lecture, next class.